I, I'm Jamesina Simpson and from the University of Utah, and I'll be focusing on the near-Earth environment, so the ionosphere down and into the lithosphere, and during a geomagnetic storm, which results from specifically coronal mass ejection from the sun. Coronal mass ejections, CMEs, there have been a number of them in our history. The largest one on record was in 1859. And in that time, there were telegraph operations over much of the continent, very long conductors. And people who were operating those experienced shocks, some of them nearly fatal. And business transactions at that time had to be shut down. Coronal mass ejections, many of them have occurred since that time. They have been smaller scale. But the 2008 National Academy of Sciences report predicted that extreme CMEs, though rare, are likely to occur again in the future. More recently, we've had some strong CMEs and geomagnetic storms on the Earth. And the most recent one that affected North America was in 1989. That one disrupted the power grid in Canada and northeastern United States for about 9 hours. So it disrupted banking and financial systems and a number of other things. The overall economic cost was about $13 million. That same National Academy of Sciences report that came out in 2008 predicted that if an extreme CME event were to occur now, similar to the one in 1859, it could have financial costs in the trillions of dollars and recovery times of 4 to 10 years. Part of that 4 to 10 years is due to power grid transformers, which older versions of power grid transformers, if they are wiped out, can take a long time to build and replace all of them. The part of this problem that I'm focusing on is in the near-Earth environment and specifically looking at geomagnetically induced currents. These are currents that result from the currents that are created in the ionosphere during a disturbed event. These are disturbed ionospheric currents, and these currents can create essentially mirror currents in the Earth's crust. And depending on the Earth's topology at that location, the conductivity, the electrical characteristics of the Earth's crust, any oceans that are nearby, these can have different electric and magnetic fields that are produced at the Earth's surface, which could then create currents that couple into the long conductors from power grids or even oil and gas pipelines. On average, about 200 days of strong to severe geomagnetic storms could produce these geomagnetically induced currents during a typical 11-year solar cycle. Many different approaches have been used over the years to try to predict the electromagnetic fields that are generated at the Earth's surface during a geomagnetic storm. I've listed some of them here. All of these methods, however, are limited to steady state or even static fields for Biot-Savart law. They use simplified physics, for example, estimating the ionospheric currents as just a line current. In this case, it was a two-dimensional problem using complex image theory. There's a single line current in the ionosphere. Actually, they ignore the ionosphere. They just have a current in free space. And then they try to project that current and estimate the fields at the Earth's surface to estimate the GICs. For these types of calculations, they have to use not only simplified sources, but also the layering in the Earth's crust is limited to just horizontal layers. And it's very difficult to account for ocean-continent boundaries. A few years ago, my group predicted that, or suggested that there are possibilities that transient electromagnetic phenomena can occur during geomagnetic storms on timescales of less than 10 seconds and possibly even less than 1 second. And this was based on some modeling that my group had done where we discovered a new coupling mechanism for ionospheric currents to electric power grids, namely so-called intra-ionosphere charge displacement. So this is a view of the northern hemisphere during a geomagnetic storm. And these pockets of red, this is showing the currents and current densities in the ionosphere, about 100 kilometers. And when we have regions of these currents flowing, we have regions of charge separation, just like in a capacitor. You have two plates of the capacitor that separate the charges. You get an electric field set up between those two plates. The same thing can happen here in the ionosphere, where we have electric fields extending between these different regions of charge. And these ionospheric currents can rearrange themselves, and there can be intra-ionosphere charge displacement and momentary electric fields set up in the ionosphere, which can project down to the Earth's surface. Now, at the time that we did this study, and we were the first to model this on a global scale and account for realistic ionospheric currents, so we were the first to suggest this new coupling mechanism, and at that time there was no published literature suggesting that there were possible hazards at short timescales. However, just recently, in the last few months, some measurement evidence has appeared. Actually, none of this data has yet been published, but I've come across it by word of mouth, and I'm working with the people who generated this data to get it published. Oops. Here is a movie that was produced by someone at NASA. This shows they went back and analyzed old data. This is for during the 2003, known as the Halloween storms, because it occurred around the time of Halloween in October. And this is a time scale of hours. The peak of the storm was around 6:58. So as we approach this time period, you're going to see these are electric fields at the Earth's surface. These are measured, so they're only going to be shown at the measurement sites. Most of them are in the northern hemisphere. And as we get to this disturbed period, you're going to see every minute. Every snapshot here is every minute, which is the finest resolution they have right now for measurements. But every minute you see the electric fields rapidly change orientation and amplitude. And they were very surprised by these measurement results that they found. And so this is the first measurement results that I've seen that point to this transient behavior that needs to be examined more closely to understand the possible hazards to electric power grids. There is one more measurement result. This is also from 2003, and I obtained this directly from someone working with the EPRI Sunburst project with the power grid companies. And the way he described it is that they were very puzzled by this measurement, where this is GIC actually recorded on a North American power transmission system node, and this is versus hours. And if we look at this time period right here, over a period of about 50 seconds, there's a very rapid change in the recorded GIC at the power transmission system node. Now, for this particular storm, there were no blackouts in North America. There were problems in Finland and northern Europe, where they did have some blackouts. But this measurement, very rapid measurement, was not even where the blackouts occurred. So the approach that we're using is the finite difference time domain method, where we're solving Maxwell's equations. And we're looking at using this model that of the Earth to not just look at transient phenomena, but also look at the longer scale phenomena that others have been looking at, but use more realistic geometries. And in order to be able to do that, FDTD is very useful because it's a grid-based method. So we have these grid cells. Here's a diagram showing one grid cell. Electric fields, this is Cartesian coordinates. The three electric fields, every electric field is surrounded by magnetic fields, four surrounding magnetic fields. And so every grid cell we can define as being a certain material, say the Earth's crust, mountains, oceans. In the ionosphere, we can put in the magnetic field, the electron density in the ionosphere, and so forth. So we can have very detailed information about the geometry of the problem. FDTD is not a new method. It's been around for quite a while. The first paper came around in 1966. As computers became more powerful, FDTD also became more powerful, especially as good absorbing boundary conditions came about. And this goes up to 2006, but it's only grown in popularity since then, especially with the optics community. So we're using a very established method for this problem. The next few slides summarize the advantages of using FDTD for this. I already mentioned where we can include the Earth's topography, and the diagram you saw earlier where we can have buildup of currents at the ocean-continent boundaries. So this allows us to look at those types of phenomena and give power grid companies and scientists location-specific information for the surface electric fields during a storm. We're solving the complete Maxwell's equations, so we're not limited to looking at only static fields or only looking at sinusoidal steady state, which I'll also get to in just a second. We can also make movies of the propagating waves and see how they interact with the different regions of the grid. Oops. As a time domain method, we can account for the time-varying realistic ionospheric currents and how they change over time, how the electron densities and structure of the ionosphere might change over time. And our grid resolution then starts to limit our time resolution. In FDTD, the time step is limited to the smallest grid cell you have in your grid. So as we try to take into account more geometry, more topography, and so forth, our time step correspondingly drops. So we're down to microsecond time resolution at the moment, which of course allows us to look at really, really short time scales with this transient phenomena. So that's one benefit. But we can obtain the spectral bandwidth if we're interested via a discrete Fourier transform. Some other advantages for FDTD, we've recently developed a stochastic FDTD, brute force Monte Carlo approaches for calculating variances of electric fields and magnetic fields. These can quickly become too computationally infeasible in 2D, especially in 3D for these large scale problems. So we've developed a numerical approach called stochastic FDTD, where we model not the propagating mean values of the electric and magnetic fields, but we also propagate the variance values. And they propagate similarly just like waves, just like the mean values do. And so one of these stochastic models takes about double the memory and double the simulation time, but that's a lot more efficient than Monte Carlo. And lastly, the magnetized ionospheric plasma algorithm that we developed accounts for all the important effects of the ionosphere on electromagnetic fields. Of course, the disadvantage of taking into account all these details in physics is that we need significant supercomputing resources, which Blue Waters can help out with. But more significant for this area is that really we're not able to provide real-time calculations. For that, we'd have to, at this point, use a different method. But our goal right now is not to perform real-time calculations. We want to understand the physics better. The Earth-ionosphere FDTD models that we are now applying to this problem have been applied previously to other applications. We've looked at Schumann resonances, detecting oil fields, hypothesized earthquake precursors, and remote sensing of ionospheric disturbances. So we're expanding now these established models into a new application area. Here's a diagram of the grid. This is the latitude-longitude version of the grid where the cells are formed by lines of latitude and longitude. We have a second generation grid that's a geodesic grid formed by hexagons and pentagons. Right now we're not focusing on that one because the magnetized ionospheric plasma is quite a bit more challenging to get going with, to incorporate that into the hexagon cells. So I'll be talking about this grid specifically. It's not drawn to scale. The grid cells actually get smaller as either pole is approached. So we have, what I've tried to show here is that we merge cells in the east-west direction. Two cells become one to try to keep all the cells roughly the same size so that our time step can be a maximum time step. So the grid is comprised primarily of these trapezoidal cells and triangular cells. Now they are three-dimensional. I only showed one plane of the grid, 5 minutes. So we have merging of cells. And then we have the Earth's topography complete in there. This is downloaded from the NGDC, the highest resolution map they have for the Earth's topography. And then we can put in the Earth's lithosphere content and variation with position. If we focus on the northeastern United States, this is available from the USGS, where this is depth into the Earth. We have the different electrical characteristics. We can account for all of that in the model. Ocean-continent boundaries, we can include those details. and Earth's magnetized ionospheric plasma, so we can account for all the important ionospheric effects. For example, the rotating of an electromagnetic wave as it propagates through the ionosphere. So I'll show a example simulation result. These are for the Halloween storms. This is the source currents that we're using in the ionosphere. And you can see that this region, the peak of the storm is over Finland. And so that's why they had some issues during that storm. I'm going to focus in here on Finland, the Finland area in Europe. This is the source currents where we're now plotting them as vectors, which I'm learning peer review at the moment to try to come up with better graphics. But what's important about this is it's very uniform. But if you look then at what our calculated electric fields at the Earth's surface, you can see that they're very affected by the topography and the location of the oceans and so forth, and you get much interesting behavior here going on. So this is the type of data that we're generating, and we're trying to understand and work with other scientists at NASA to understand and get this data to predict the possible implications for power grids. So here I've listed a number of advantages of using blue waters in our research. Not only can we use a higher resolution to account for the Earth's topography, but also we have realistic currents in the ionosphere. It's important at these frequencies to model global propagation because at low frequencies these waves can propagate completely around the world, as well as the more localized transient behavior, ocean effects, and so forth. We can account for all of these. The Blue Waters team has been tremendously helpful, particularly Galen, in helping us. He helped us implement a non-blocking in part of our sending and receiving in part of our code, which resulted in a 4% speed up. He's answered a number of questions very quickly and helped us locate and solve bugs and test out different compilers and et cetera, many other things. So that's been tremendously helpful. And recently I was invited to be one of 20 international researchers to be part of the NASA Living with a Star Working Group Institute on GICs. We met in March for the first time, and 6 collaborative research projects came out of this group meeting, which we're working on actively this summer. One in particular, for example, we're looking at the optimal spacing of magnetometers that we need to be able to predict GICs. And finally, one of the products that we're working on is to provide an FTT Earth Model that we can provide to the NASA's Community Coordinated Modeling Center that would be publicly available to anybody. They could run it and request simulation times and generate their own data for their own problems. So thank you very much for the access to Blue Waters, some acknowledgements for this, and acknowledging my NSF Career Award as well, which is supporting this project. And we have other related research projects that are going to benefit from this work because they're modeling also wave propagation around the world, but for different applications. Thank you very much.
Time for quick questions.
Is there a need for adaptive refinement of these meshes? Looks like some places there's a lot of activity and some places are quiet.
We have used some adaptive grid resolutions, particularly around the Earth's topography, right around the Earth's surface. But yeah, if we know ahead of time.
I was thinking more dynamic.
Dynamic. That's an interesting problem. I haven't seen that implemented in FDTD before. It could pose some challenges with stability, but that's an interesting idea.
We'll take more questions. While I take them, I would like to do the switching of the machines. Can you please help the computers? Okay, next, who had them on there? Yeah.
My question is probably similar. So in the ionosphere, I don't know how detailed the model is, but you just inject currents, or do you also have, because if you have like particles coming in and you get changing the conductivity, so there's a couple of systems that affects the ionosphere. I just wondered how detailed the driver was in the ionosphere.
Well, yeah, we're starting out with just modeling the currents themselves. It's not dynamically changing, responding, but that certainly could be a next step.
Yeah, well, my question was almost the same. It was about the source model that you use? Or?
Well, we account for the magnetized plasma, but yeah, there's not yet any dynamic, the communication's one way.
But the source currents, where did it come from? Is it some kind of
Oh, yes, that's a good question. So far we're using BAS-RF data. There's a hope in the future to be able to use Ampere data, which is measurement data, from the project Ampere at Johns Hopkins. That's what we're working with so far.
Any final question?
You mentioned you're not running global scale yet. What milestones would you have to hit before you were confident enough to start burning time modeling at a global scale?
Oh, we are actually modeling at global scale. I don't know, I didn't mean to mislead, I don't know what I said, but we are modeling at a global scale. We're overcoming some last hurdles to refine the resolution as much as we would like to 1 kilometer resolution. We're at the last hurdles to that. Just in the efficiency of the polar regions make it a little bit more challenging to put the same number of work on each processor. But it can run right now at global resolution, high resolution.
Okay, thank you.
Thank you.